As Bruce mentioned, I held my first meteorite in 1996, and there's something tactile about your connection with reality. Holding a meteorite in your hand says something important to you. You feel it and you understand it in a sort of an elemental level. And from that initial introduction to meteorites, I bought more of them and I studied them under microscopes. I read volumes and volumes of stuff on them, and I've collected quite a collection of them. So most of the pictures tonight, except for the huge specimens I have occasional photographs of, most of the specimens are my own collection. So let's get on with it. So meteorites. Have you ever seen a meteor? Well, I assume that out there in the Zooniverse, people are probably well aware of seeing little streaks of light across their skies at night. Here's a shot of the Leonids. The Leonids were incredible in 2001. It literally did look like the stars were falling out of the sky. It was fantastic. But stars aren't really falling out of the sky. People really actually thought that was the case, though. It was a kind of a neat thing. Historically, people thought meteorites were produced because they were associated the rumbling of thunder in the sky with meteor falls, or they're produced by volcanoes. And at that time, of course, they hadn't discovered asteroids yet. And this woodcut here is Ensisheim on November 1492, same year as Columbus went out and found the New World. Well, the space world was finding us at the same time. Inevitably, facts went out. In France in 1803, meteorite showers of about 3,000 stones in the town of L'Aigle in Normandy, France, was pretty incredible. It was hard to deny that this thing came out of the sky. And Jean-Baptiste Biot studied the fall, and his passionate paper describing these stones, undoubtedly expressing the extraterrestrial origin of them, gave birth to the science of meteorites. And by the mid-1850s, meteorites being an extraterrestrial phenomenon was widely accepted. Biot is widely known for the Biot and Savard law of magnetics. He's a physicist of some renown. Well, meteorite showers, the ones that we typically see, the Leonids, Perseids, others, they're typically made up from breakup of comets. And when you have comets, you have an ion tail, blue tail pointed away from the sun, and a dust tail that is dragging behind it. And the dust tail is composed of silicate dust grains. Some of the dust grains are actually fairly big, and these grains, when they strike our atmosphere from a smeared out comet tail, produce the lovely light shows that we have of the Perseids, Leonids, and things like that. The Perseids are from the breakup of comet Swift-Tuttle, just for your information. And we know meteorites are also from the breakup of asteroids. Some are from the moon, some are from Mars. And a lot of people come to me and say, well, how the hell do we know they came from Mars? Well, we can see the craters on Mars and know that the craters are capable of launching material into space. But back in the late 60s, early 70s, we put a lander on Mars, and our first lander on Mars had a mass spectrometer on it. And it measured the isotopic ratios of the gases in Mars's atmosphere. And the blue line on the graph is Earth's terrestrial fractionation line, because the solar system acted as a gas fractionator. The materials, as you went farther out from the sun, differentiated because of the gravity well of the sun. Well, scientists analyzed gases trapped in vesicles in meteorites and found they matched the isotopic fingerprint of the gases on Mars. And you can see a couple different Martian meteorites above in red and in blue. And this is definitely a really cool thing, showing where these things came from. Statistics, well, there's a constant rain of meteoric material, 100 to 1,000 tons per day. And that sounds like a hell of a lot. You'd think you'd be up to your knees in it. But if you think about the fact that the Earth's got about 2 billion square kilometers of surface area, it's pretty easy to put away 1,000 tons of dust. You wouldn't even notice it. It wouldn't be even a significant level on your coffee table. Meteorites come into the atmosphere of anything from 12 to 70 kilometers per second. And if they're smaller than a gram, they usually burn up. Of those that make it to the ground, less than 5% of the original mass is left over after it hits the ground. In other words, 95% of it burned up on the way in. Stony meteorites develop a black fusion crust, like this creature to my right. And this one has got beautiful flow lines on it. This is probably a eucrite. They form a nice, they almost look like they're dipped in honey. They're wonderful. And meteorites that are bigger than 350 tons hit the ground with most of their original speed. And they make a heck of a mess when they hit the ground. They usually dig out craters. And there's one thing, people usually think that meteorites are going to be hot when they hit the ground. And this, in fact, is not true. The next slide is going to show a few, it's a slide farther down. I will attend to that, the cool to touch business in 2 more slides. But one of the things, there's always rumors that somebody's been killed by a meteorite, but there's no documented evidence throughout history of somebody actually being killed by a meteorite. There's proof that a cow was killed by a meteorite, and they claim that the Nakala meteorite actually killed a dog, but that one has been disproven. So interesting stuff. People have been hit by meteorites, and that is an interesting case. And in fact, one of your BC residents narrowly missed getting knocked on the head by a meteorite that landed next to her on her pillow in Golden, BC, about a year and a bit ago. Well, if you see a bright meteor, and I'm talking about something brighter than the Perseids or Leonids or things like that, try to guess how bright it was. The bright stars in the sky are mag 101, with Sirius being at -1. Venus's magnitude -4 to -4.8. Full moon -12.6. Sun, of course, is -26. Well, if it's brighter than -10, there's a good chance it might actually put rocks on the ground. So then it's good to pay attention to where you saw the meteor going, what compass direction it was, how high off the ground it was. Try to keep these ideas in your mind, and then you can make a report that will help people find and recover it later on. Here's the slide I was talking about, Meteorite Fall. Well, a little meteorite, and I don't know if you can see my cursor. Somebody can chime in if you can see my cursor. Little ones like the Perseids and things like that, they actually burn up and don't even make it very far down into our atmosphere. 80, 90 kilometers is about where they peter out, but they're really fast and they produce brilliant streaks across the sky. A typical meteor that might hit the ground comes in, it heats up a bit in the outer tenuous chunks of our atmosphere, and at about 80, 90 kilometers off the ground, it starts becoming luminous. And somewhere above 40 kilometers off the ground, it starts fragmenting. It'll break up into pieces if it's got any weaknesses in its structure. Remember, these things are moving at something like Mach 30. The hydrodynamic forces on them are so incredible. They're trying to tear the meteorite apart, and they're usually successful. Most meteorites fragment on their way in. Somewhere down around 30 kilometers off the ground, luminous flight ends. And that's about where ablation ceases. The luminous flight is where the material is being ablated off the meteorite. And then it starts its dark flight. And its dark flight will carry its trajectory in that same direction that it was coming down for a while. And then finally the winds slow it down so that it's actually moving at a ballistic trajectory. And the winds can actually steer it back on its course, drift it east, west, who knows. But the material that was coming off the meteorite and the fragmentation and stuff falls and forms something called a strewn field. Now, if a meteorite flashes across the sky, and from reckoning it was only 10 degrees above the horizon, i.e. a fist at arm's length, we want, and if it went dark 30 kilometers above the ground, how far away was it? I'll let you think about that for a millisecond or two, and then I'll actually give you the answer. Well, turns out the tangent of 10 degrees is height divided by the distance. And so we can relate the simple formula: distance equals the height above the ground that you think it went out at, divided by 10 of 10 degrees. And it turns out if it's 30 kilometers off the ground, the tangent, and I've got it listed as 15, but that's just in fact wrong. I did use 10, is about 170 kilometers. And with the it following its trajectory, since you're seeing it low on the horizon, it was going away from you in the first place. So it could be as much as 200 kilometers away. So in the case of the Buzzard Coulee meteorite that happened west of or east of Edmonton, people saw this thing come down, and it was 10 or less degrees above the horizon when it went out. And people in Edmonton thought that it was just in the neighboring community 20 kilometers out of town. And they were ready to get in their cars and drive out and look for it in the ditches out of town. It was just amazing. But it turned out it was actually 300 kilometers away in Saskatchewan. That's how far away these things can be. The only time you're going to have a meteorite fall somewhere near you is if you didn't see the fall at all. It was above your head, and the stones will come down somewhere nearby. Pretty cool. Well, I talked about a strewn field. A strewn field is associated with something called a distribution ellipse. And this is a plot of the Bruderheim meteorite that fell in 1960. Now, this one formed an elliptical distribution. And you can think that when the meteorites break up in the atmosphere, they break up into small pieces and they release a lot of energy. And it causes braking on the flight of the path. But these particles that are floating in space, they form a spherical distribution around the axes of the thing was coming in on. And when they hit the ground, well, it's like a beam of a flashlight. If it was straight down, it'd be a circle. But if it's at an angle, it's always going to produce an elliptical distribution of material. So kind of cool. And where do these darn things come from? Well, Canada has some fame in the game. We had the meteorite orbital parameters cameras that were set up in Alberta, Saskatchewan, and Manitoba. And through all of the data that they collected, they found 3 meteorites with well-defined trajectories that they actually managed to pick up off the ground. And that's Fiberon, Lost City, and the Innisfree meteorite. And they could take the trajectories that they found from 2 cameras, can find the intersecting planes of the meteor trajectory as it came in through our atmosphere. And then they actually had a stroboscopic camera so that they could chop up the meteorite trail into 1/50th of a second increments. And so they could tell how fast it was moving, and they could get all of this important data. And then they could project the meteorite backwards out into its orbit into the solar system. Really, really cool stuff. We're doing more of that now with some more sophisticated equipment that's come out of Australia. Okay, down to the group. We've got chondrites. Everybody's probably heard of a chondrite, and chondrites have chondrules, and chondrules is a Greek word for a grain of wheat, grain of sand. It was a chondrule. Well, we call the little round bodies that are inside these meteorites chondrules, and that makes them chondrites. And this is the stuff of the primordial solar system. The silicate, dust, and metal that was floating around in our solar nebula crystallized out And there was a point at some time in the very, very early solar system where there was a heating event. And the heating event was enough to melt silicates, but not the nickel iron crystals that formed. So the nickel iron crystals look like little snowflakes and stuff like that, but they didn't melt. And the silicates did, and they formed these little round bodies. And this photomicrograph on the left shows this beautiful chondrule with a particular crystal structure. It's called barred or radial formation in the chondrule. And the really neat thing about these things, if you ever hold a chondrite, you're holding the oldest material in the solar system. It was formed 4.56 billion years ago. And as was pointed out by a friend of mine, Bruce McCurdy, it's also one of the newest rocks on Earth because it wasn't here yesterday, it's here today. So that means that it's one of the newest rocks, but it's the oldest material in our solar system. Cool stuff. And this is a shot of a cross-polarized image of a slice of the Buzzard Coulee meteorite. And you can see from the colors, they can tell what different minerals and stuff are in this slice of meteorite. Well,
Murray.
Yes, sir.
Murray, yeah. Could you tell us how large was that meteorite with the striations and the radial striations? Do you have any idea?
The chondrule itself?
Yeah.
The chondrules themselves are in the millimeters. Some of them are as much as 5 millimeters in diameter. Sometimes they're down to 1/10 of a millimeter in diameter. So the chondrules themselves are actually fairly small. In this photograph, the big chondrule on the right is probably about 1.5 millimeters in diameter.
Okay, so that was that circular thing was a chondrule, not the whole meteorite.
No, that's right.
Yeah, okay.
Yeah, and the colorful portions are other portions of that same meteorite. There's another chondrule that's entirely opaque down below the one on the right. And there's some other spherical objects in this, and some of them are possibly chondrules, but since I did not take this slide, I can't verify that. Okay, back to Stony meteorites, number 1. Chondrites, well, there's enstatite chondrites, olivine bronzite, hypersthene, and carbonaceous chondrites. And the olivine bronzite are high H-type chondrites, which stands for high iron, 15 to 20%. L chondrites are the medium iron, and they're 7 to 11%. And the LL meteorites are the very low iron, and they're 3 to 5% iron. And if you pick one up with a magnet, the H chondrites, they stick to the little high energy magnets that you can get at Lee Valley Tools or in Princess Auto. They stick like crazy. It's just amazing. But when you get down to the low iron content, the LL meteorites, they don't stick very well. You can shake them off real easy. But it's a nice way of being able to tell what you've got in your hands. The carbonaceous chondrites are a little bit different than the other ones. They, instead of having heat treatment that metamorphosizes them, they can be altered by water as well as heat. So they also contain silicates and metal. And there's C1, C2, there's CI, CM, CO, CV. These all stand for the particular primal meteorite of that species that was found on the Earth. A CM is a Murray chondrite. These were the first incidents of a meteorite having a particular structure was named after the town or rural area that it was found in. And there's the CV is Vergano, CI, I can't remember, CO, they escaped me at this point. Stony meteorites, we've got H or L or LL. They also come with a designation of the state of metamorphic alteration. the gravitational pressure in the asteroid body that they were formed in causes them to metamorphosize. And I'll use the L meteorites for an example. An L3 is pristine. It's almost unaltered. And in fact, people have found meteorites that they call L3.0s. They're almost no alteration whatsoever. They're pristine solar material just from the first elements of the solar system. L6, well, as you go up in size, the alteration becomes more and more. L6 chondrules have been altered to make them quite indistinct. They're not as good. L7, the chondrules may be almost completely erased. And this goes for H, Ls, and LL meteorites. And I'll show you some pictures of them. The chemical abundances, of course, are much like the sun. Surprise, surprise, we come out of a solar nebula. So the material that makes up the planets and the material that is in the sun is very similar. And actually what we believe is that a supernova caused an impulse of pressurization which destabilized the nebula around where our sun formed and caused it to condense into a solar system. And so the supernova actually injected some material into this gas cloud and seeded it with some heavier elements and some other interesting things which I will mention as we go along. And here's a Buzzard Coulis meteorite. This is one of mine. On the picture on the left, you can see the shiny metal content that's in it. There's a lot of nickel iron that's in this, and the little flakes are typically in the millimeter size. Some of them are even bigger, like a couple millimeters, but they're mostly small. And in the photograph on the right, you can see the chondrules, the little round bodies that are in this. It was quite exciting to see this when I first found these meteorites. And down below, there's a broken face on a Buzzard Coulis meteorite where you see a white chondrule and then some yellowish ones. And the other photo shows even more. It's really, really cool. When you find a meteorite, if it's got broken open surface, you can tell right away what kind of stone it is. And your magnet will tell you what level of the material is. So here's an H5 Gao meteorite, and you can see the metal in that one quite nicely. And Northwest Africa is another place that has some really nice meteorites coming out of it. This one, this is beautiful. This is a pristine L3 meteorite, and you can see just tons and tons of chondrules. It's just packed with every space within it with chondrules, and it's just amazing. Quite a beautiful meteorite. And then we get, that was an L3. This is an L6 chondrite, and you can see from Shizu Chinese meteorite on the right, upper right, that the chondrules are quite indistinct. There's one nice dark one that seems to have survived really well, but most of the chondrules are sort of really washed out. And you can see some big metal flakes. And you'll notice that there's not a lot of metal flakes in the L6 meteorite. And below it is a photograph of Bruderheim, Alberta meteorite. And this is a 100-gram specimen. Okay, the Richfield Chondrite, as I said, it's got beautiful colors in it. The chondrule, this massive, huge chondrule up in the upper left corner of this upper specimen, it's got a pale blue rim with a darker blue interior, and it's just chock full of chondrules when you look at it carefully. If we go down to the bottom of the page, you can see the nickel iron in the lower specimen, and you'll notice that it's not as dense a concentration of nickel iron as was in the Buzzard Coulis. And this one, it sticks to a magnet, but only a little bit. The chondrite on the right-hand side of the photograph is the Tuksu meteorite from Mexico. And this is an LL6. And the chondrules, they're not as distinct. There are some of them that are still fairly good looking, but they're not as distinct. The story about the Tuksu it fell, and the Mexican locals that found this thing back in the hundreds, thought that there must be gold in it. And so they broke all the meteorites up trying to find gold in them. And there was no gold in them, they were just iron. Okay, there's the February 15, 2013. February 15th is a special day. It's the day after Valentine's Day, and it was one heck of a Valentine's Day gift one day late. The world's astronomers were watching a 50-meter asteroid pass between the Earth and the Moon. And meanwhile, a 15-meter meteorite snuck up and exploded above Chelyabinsk, the USSR. And in the photos on the right, there's 4 specimens that I've got there and a jar of little tiny peas, little Chelyabinsk peas, really kind of cool. This meteor was 15 meters in diameter, and I did a quick calculation, and it's between 5,000 and 6,000 tons that this thing weighed when it was coming into the atmosphere. This thing exploded with the energy of about a half a megaton bomb, about 30 kilometers above Chelyabinsk. And if this had happened during the time of detente between the US and Russia, Chelyabinsk was a place where they were processing nuclear materials for nuclear weapons. And I'm sure that this would have started a war. It's just amazing. It's scary to think about it, but fortunately, the world was a little bit quieter of a place. It might not have fared so well this year if it had happened. Carbonaceous meteorites. The designation is followed by a number that represents the state of metamorphic or water alteration. And the CV, the Vergano meteorites, I'll use as an example. The CV3 is pristine, almost unaltered material. The CV2 has been altered by water. A CK6 has had metamorphic alteration, and heat and stuff have changed the structure of that meteorite. And here's some carbonaceous chondrites. And pay attention, BC has got a contribution here, the Tagish Lake Meteorite. These are Tagish Lake Meteorite crumbs that I bought from a gentleman that was up in the Tagish Lake area, who picked over the area after Alan's Hildebrandt's team left. And down below is the Allende meteorite. And at the time that the Allende meteorite came in, I think it produced about a half a ton of meteorite stones that were recovered. And it represented more than half the world's CV or carbonaceous chondrites at the time, because there were so few of them that had been found. And neat part about it is that you see this big white blob on the corner of it. This is a calcium aluminum inclusion. And the calcium aluminum inclusions contain little needles of titanium oxide and other material that could not have formed in our early solar system. It had to have been expelled from the supernova that started and was the progenitor of our solar system. So these materials are actually older than our solar system. And I have not seen an age specified as to how old they found these things to be. Really, really cool. And this little fellow on the lower right is a Murchison meteorite. This fell in Australia, and they've discovered about 70 different amino acids in it. Amino acids are, necessary for organic life, but organic molecules can form in a test tube or in interstellar space. And so this Murchison meteorite has quite a number of these, amino acids in it. It's really quite cool. And the Gushba, which is just above this and on the very right-hand side of the pane, for some reason, it had these big metal blobs in it and carbonaceous material interspersed in the matrix of the unit. Really, really fascinating meteorite. And now we're going to go from the Stony meteorites to the chondrites. And a chondrite means it's not a chondrite. That's all it means. And in fact, if you think about it, Earth rocks are chondrites because they're not chondrites. So back at the ranch, there's Aubrites, Diogenites, Chastanites, Uralites, Angrites, Nacolites, Howardites, Eucrites, and they all are classified being calcium poor or calcium rich or basaltic. And we'll see these guys in a few minutes here. On a planetary or terrestrial kind of a body, you have an iron core, which has iron sulfide and nickel in it. And then there's an outer core, and then there's a mantle of basalts, pyroxenes, olivines, and stuff like that. And then the crust, of course, is the hard part of it. It's feldspars, micas, quartzes, granites, stuff like that. In the asteroid world, well, they never developed an atmosphere or weathering. And what happened to them is that the core, it's like the Earth's, it's a nickel iron core. And the core mantle boundary, or I should say, let's get into the mantle. The mantle is a chondrite diogenitic kind of material. The core mantle boundary is a stony iron material, and this is pallasites. And pallasites are the crown jewels of the meteorite world, but we'll get on to that later. The surface of the asteroids, well, their volcanic lavas flowed out and formed the surface of some of these asteroids, and then they've been pounded unmercifully by other asteroids and meteors throughout their time in the solar system. And so what's happened is that we've built up something akin to a soil on the surface, and we call the meteorites that express this Howardites, after the first one that was found. And this material, what happened is meteorites were pounding these asteroids, and then the material sank back down onto the surface. And as that material built up over time, the compression of it caused the material to form, become hard. And so we get these meteorites that are actually from this area of the asteroid. So it's pretty cool. Earth, Moon, Mars, Vesta series, they're all examples of terrestrial planets. And here's the asteroid series. You can see that it is literally like the moon. It's just been pounded by meteoric impacts over time. And one of the neat things that scientists have done in their time of examining meteors and examining the asteroids is that they've taken both and had developed infrared spectra going from visible light all the way out to far mid-infrared wavelengths, because we can do that with our telescopes down here on the ground. And they've compared the spectra of meteorites that we found, which are on the right, with the spectra of asteroids in the asteroid belt. And you can see the similarities in the infrared spectra. And you can say without much doubt that Vesta's got a lot of eucritic material in it. Eros probably has a stony iron kind of constituency, and Psyche and Ceres quite possibly have carbonaceous material on them. I think Psyche might be a metallic as well. But anyway, it's really quite cool what we've discovered with our scientific instrumentation. And so here's some asteroid fragments from Johnstown meteorite is a diogenite monomict. It's brecciated olivine. A monomict means it's a mixture of all the same material. There's green crystals of olivine, there's powdered olivine, and it's all throughout it. And you can see little brown spots on it. There are the occasional fragments of nickel iron that are embedded in this, and they have rusted from their time on the Earth here. And over on the right-hand side, we have the Pina Blanca Arborite. And this is a beautiful meteorite. I'd love to have a countertop made of this stuff. And but just gorgeous material. And once again, you can see a few brownish spots on it. Those are from the nickel iron that is interior to this material, but you can see that it's incredibly sparse. You cannot influence these with a magnet whatsoever. So hunting for them with a magnet would not make a lot of sense. Well, eucrites. Eucrites are, remember, they were the interior material of the asteroid. And the Millville Lily was an asteroid or a meteor that fell in Australia and was discovered a few years later. And it's got this beautiful glassy crust. It's black. It looks like it should be wet to the touch, but it's not. And the interior of it's this cream yellow colored material. The material is down inside those asteroids. And the Camaldonga is another nice little eucritic meteorite. And once again, it looks like it's got honey on it. You know, it looks like it should stick to your fingers when you pick it up. And then we go on in our voyage of chondritic meteorites. There's Marsha Meteorites, there's Shurgatites, and these are, this one is Tissant. This one actually fell in Morocco about 10 years ago. And it's got a beautiful glossy crust, and its interior is gray colored. The Shurgatites, there's a Gamma meteorite, which is on the right upper corner. You can see the pigeonite grains in it. And this meteorite was landed in Castinga, Nigeria, and a local farmer was plowing his field, and this thing came down with like about 100 feet away from him, and he retrieved the stone, and it ended up in the museum in that country. And then a number of years later, Robert Hogg, a famous meteorite pirate, went to Nigeria and spoke with the director of the museum, and he showed him some beautiful flashing meteorites, some absolutely stunning pallasites from the Escal meteorite and a bunch of other just absolutely beautiful meteorites. And he traded those meteorites for 1/4 of the Zagami meteorite. And the Zagami meteorite, at the time that he came back to the US with it, wrapped in a towel in his luggage, I think he had about 1,000 grams of it, maybe a little over a kilogram, maybe 2 kilograms of it. It was worth $4,000 a gram. So you can do the calculation. Now, he became quite rich instantly because of that particular meteorite. In the bottom, we've got Basaltic Breccia. This is a new variety of Martian meteorite that was recently recovered in Morocco. And it's got a really interesting crust. And then if you slice it open, you can see these little spherical particles in it. And those spherical particles, remember the blueberries that they were finding with the landers on Mars? Well, these are blueberries that haven't been eroded out of the material. So really, really cool stuff. And on to lunar meat. Well, of course, Moon is really close to us, and it's impacted like crazy with meteorites. And so some of those have projected rocks in space that have orbited the sun for a long period of time, or the moon, and they've eventually crashed into the Earth. And to date, 371 meteorites from the moon have been recovered, mostly in the hot deserts of the world or in Antarctica. And so there's a couple nice meteorites shown in these pictures. NWA means it's Northwest Africa. So it's Morocco, Mauritania, Algeria, Libya. And they're beautiful specimens of brecciated structure. And here's a few specimens from my collection. Lunar Meteorite 1123 or 273, Lunar Feldspathic Regolith Breccia, Daralgani 400, and Northwest Africa 10205. Just beautiful little slices of the moon. The Stony iron meteorites, remember we said that there was a core mantle boundary that you form something called Stony iron meteorites or pallasites. And what happened as the asteroid cooled off, the nickel iron core finally started to freeze up. And as it was getting close to freezing up, the material on top of it, there's an interesting phenomenon that happens when you have a phase change in a material. There's turbulence that develops at the boundaries of it. And what happened is it entrained some of the crystals that were precipitating out above it in the magma area. And turns out that the heaviest material in that magmatic area is olivine or peridot, and which is the name that's used in the jewelry industry. And so these are filled with peridot. It's really, really quite cool. And on the left-hand side, there's the Shimshan meteorites from Russia. There was a bunch of beautiful stones that have been found. This is a nice stable meteorite. There are a whole bunch of different palasites that are out there, and some of them are so unstable you'll buy them and they'll rust and they'll turn to rust and crystals falling on your desktop in 5 to 10 years time. Others are beautifully stable, and the Shimshan is beautifully stable. The Immalaq palasite that's shown on the right, it is also beautifully stable. I've had this specimen since the late 90s, and it's a beautiful little unit. The little piece above it is called an Immalaq skeleton. And what's happened is this was left in the desert and it was on the surface. And so the olivine crystals that were within it rusted out, or they eroded out, and the iron has since rusted somewhat, but it's probably been around in the deserts for 1,000 years or a couple thousand years. And it's amazing that it's only rusted that much. The next slide, a Canadian and an Argentinian palacite. The Springwater, Saskatchewan is one of Canada's important palasites. I don't know if there's another one in the Canadian collections, but I've been to Springwater, Saskatchewan, and we surveyed the countryside around there. A gentleman was mining the area for meteorites at the time, so he tied up all the land and we couldn't go hunting for it. We may go back and try to do that again someday. But anyway, this was a nice specimen that was in my collection. And on the right-hand side is the Escal Palestine. And as I said, this is the crown jewels of the palasites. It has beautiful green, transparent olivine crystals in it. And it's just gorgeous. This piece is about the size of a business card. And it's only a couple millimeters thick. There's another type of stony iron meteorite, and these are called mesosideroids. And what happened on the asteroidal bodies where these were formed, these bodies had formed, they'd cooled off, and a core from a planet, a small planet, was exposed and ran into another small body. And what happens when things hit? Well, they get really hot, they melt, and they intermingle the iron and the eucritic material that was in that other asteroid body. And so you end up with these little blebs and blobs of iron inside, and the Escherville has got fairly macroscopic blebs and stuff in it. And the Vaca Muerta, which is from Chile, it has finer little traces of nickel iron in it, against a eucritic background in it. And these are both in my collection. And this is just a closer look at the Vaca. You can see the little areas where the nickel iron is inside this thing. They just polished a window on this one. They didn't cut it and polish it. On to other chondrites. Well, obviously the cores of those planets are chondrites, and we've got a number of different type of meteorites called octahedrites, and octahedrites have an octahedral crystal structure, and that's why they're called octahedrites. And I'll show you a slide in a few that explains this. But on the left-hand side is Gibeon iron from Namibia. It's a fine octahedrite. It's about a 5 kilo stone. And the white cord iron meteorite on the right-hand side is a medium octahedrite, and it's 330 grams. And why are they called octahedrites? Well, I said there's an octahedral crystal structure, and these slices of meteorite show that octahedral crystal structure to some extent. And the Gibeon iron, which is in the bottom left quadrant, you can see that the lines are smaller than a millimeter wide. I believe that these squares are 5 millimeters across on this. So you can see that there's the lines in the Gibeon, they're smaller than 1 millimeter. And why do these things form one size or another? Well, what happened is different asteroidal bodies had different amounts of aluminum-26 and other things in it. So the decay of the radioactive aluminum-26 caused the asteroid to retain heat longer. And some of them had more of it, or some had less of it. And so some of them cooled down quicker than others. And the ones that cooled down quickly, the patterns became really fine. The crystals didn't have as much time to become gross and large. And you look at the Cape York meteorite right above it, you can see that the bandwidth on that is significantly bigger. These are all almost to the same scale. You can see from the pattern of the 5 millimeter graph paper behind it. And then the Toluca that is on the right-hand side, you can see that these bandwidths are even larger yet. And what's neat in this is you can see that there's other material in here. There's other crystal structures that form when you've got nickel and iron. You can get complex molecules called schreibersite. And there can also be impurities like the black dots in the Gibeon iron on the extreme left. These are actually iron sulfide spots or carbon. I'm not sure which those ones are over there. And now for one of the biggest meteorites in the world, in Namibia, and it's called the Hoba iron meteorite. It's 60 tons and it's roughly rectangular. It's about 1 meter thick, and nobody's ever been able to move it. People have sawed corners of it off and put them in their collections or taken them to museums, but this thing has never left. And so they built a amphitheater around it, and they occasionally buses of tourists show up and they give a talk about the meteorite. In this photograph are some notable members of the Royal Astronomical Society of Canada, Doug Hube and his wife. And Doug, I believe, is a vice president or something of the society. Charles Ennis will correct me sometime on that. No, not at this point. Okay, you can correct me later, Charles. Thank you. Anyway, meteorites and their impact. Well, when meteorites come to the ground, sometimes they're big enough that they dig craters. And if they're small enough, they just create a plunge pit into the ground. A lot of meteors will end up in the ground. They'll go down 1 to 2 meters in depth and finally stop in the soil. Some are big enough that when they hit the ground, they release enough energy from either the disruption of the meteorite or from the fracturing of the meteorite and it's splitting into millions of pieces to dig out a crater. The heat of vaporization was enough for the meteor crater Arizona for the 90 million tons or billion tons of iron that they thought had come in to create that crater. It all evaporated. It completely evaporated. There was a thin patina of iron dust out to 20 miles away from the crater. It was amazing. The meteor crater that was formed at Whitecourt, Alberta, the meteor actually shattered, and the shattering caused it to rebound, and it dug out a 37 meter diameter crater in the process. So it's really interesting. But the takeaway from this is that most meteor craters, as the ones you may have seen on the moon, they have an uplifted bowl shape, and that's from the material that deformed the ground structure and was ejected out to create ejecta layers on the outside of the craters. Now, where do these things come from? Well, crossing asteroids. There are the Amurs, Apollos, and the Athens. And these asteroids dip, the Amurs only dip within the orbit of the Earth. The A10s, actually, the Amurs almost make it to Earth. And so some of them must eventually make it in. The Apollos, they just cross the Earth's orbit. And the A10s, they actually go all the way in to Venus's orbit. And I think, yeah, the Apollos do as well. So these cross the Earth's orbit, and we have to watch for these guys all the time. Like the one that came from Chelyabinsk, if it had been 100 meters in diameter, boy, it would have caused a lot of trouble. So Whitecourt, this happened, impacted the ground about 900 AD, and it dug out a crater 37 meters in diameter and created an ejecta blanket around it and deposited the shattered remnants of this meteorite in a halo around the crater. There's actually about 3,500 data points that a team that I was involved with recovered meteorites from this area. And so we've developed a really good map of the strewn field. And these are some of the specimens from Whitecourt, Alberta. And I'm comparing one from the Gebel Camel crater in Egypt. It formed a very similar crater. And you can see some of the pieces have even similar structures to the ones that are found around Whitecourt. And there's a broken heart. You can see that it was rend by the impact. And you can imagine the incredible forces on this stuff that would have torn the iron up into these kind of pieces. It's just crazy, just amazing. And down below, there's a sliced and etched pattern from one of the Whitecourt iron meteorites. And this one, you can see the triangle of the octahedrite cut off in the way the material is oriented. And over on the right lower is actually an individual, small individual of this meteorite. This is a 331 gram specimen. And you can see the regmalips on the surface of it among the rust and other stuff that's formed on it, and the caliche that's formed on the surface. Cool stuff. This is a photograph looking east from the upper west side of the crater, looking out across it. And this is from the opposite side, looking to the west, but in a different season. That's my wife down on the bottom. But you can see how tall the walls are on this. And we organized a tour of the Whitecourt for the General Assembly a number of years back. I think that was 2013. And it was quite fun. A lot of people got a chance to go out, see the crater, and actually even go out and hunt for a meteorite. It was really cool. Shigori Helen is another big meteor that came in. It was in 1947, and it was 2 days before Valentine's Day, in February 12, 1947. And 25 tons of iron came in, and it broke up in the atmosphere and created 385 craters. The biggest of those craters was 20 meters in diameter. And you can see in the photograph on the right that a trunk of a large tree was actually thrown up into the top of a neighboring tree. Just amazing. And in the photographs of the meteorites themselves, the one on the upper right, this was an individual that broke off in the atmosphere and made its way down by itself. It's actually got little rivulets of molten iron that ran down the side of it like raindrops on a windshield. It's really quite cool. And it's got some regmalips that are developing on it. And the other piece down here is a piece of shrapnel. And this is sharp. You can almost cut yourself on it. It's quite neat. And another place I managed to get to in my wanderings is the Henbrite Meteorite Conservation down in Australia. And we went down for the eclipse in 2012, and so I had to go out and see the craters. I mean, you've gone this far, you might as well go a little farther. And in the conserve, there's about 13 craters in this grouping, and the biggest is the one here up at the top. And it's an enormous crater. It's 182 meters across, and it's about 15 meters deep. And you can see the tall trees growing down in the crater that are actually below the level of the rim. It's quite neat. It's fun to walk around this area. It was only 43 or 46 centigrade that day. And we went back to the Alice Springs Museum, and they had a bunch of the Hanbury specimens in the museum. And here's an 85 kilogram specimen that was found and donated to the museum. Really, really nice looking specimen. This is the 312 gram specimen that's in my own collection. And they form the weirdest shapes, the individuals that came down. It must have broke up in the atmosphere, and there were literally thousands of little pieces of it that came down among the 13 big pieces that came down that were crater forming. And speaking of craters, well, the biggest in North America that's, or biggest in the US, is Meteor Crater, Arizona. It's the most well-preserved meteor crater, I think, in the world. It's quite beautiful. And it's about 1,100, almost 1,200 meters across and 173 meters deep. So anyway, there's the Meteor Crater, Arizona. It's beautiful. If you're in Arizona, go to it. It's beautiful. It's really awesome to stand on the rim of that crater and look down across it. In Canada, we've got the Immalaq Crater, which is 3.5 kilometers in diameter. It's about 1.4 million years old. It's in northern Quebec. And we have the Manikugen Crater. And this is 90 kilometers in diameter. And I think that I've got to do a check. I think this is the largest impact structure that's visible left on Earth. I don't think there's anything bigger than this anywhere on Earth. So I'm going to have to research that one. It's really cool. You can canoe around this thing if you want. It is, but it's just enormous. I've talked about meteorites. I'll quickly go through things that are not meteorites, but caused by meteorites. And tektites were actually ejected out of some of the meteor craters that have happened on the Earth. And what has happened that when the meteor struck the Earth, it flash melted the soil and sand and ejected it in streams off into space. And this stuff did ballistic arcs and came back down thousands of kilometers later. And so there's Indochina tektites. There's Moldovite tektites from Czechoslovakia area. They were formed by the Rise crater in Germany. Zamshin crater glass. This is found very close to the crater. This is about 3 inches square, this little box that's holding them. Bilonite tektites from the Philippines. They've got these deep grooves in them. They look like soccer balls. Flanged buttons from Australia. Beautiful little delicate things. Livians of glass from the, somehow formed by a meteorite, but there's no crater associated with this. So we haven't figured this one out completely yet. Questions? I'm done. And apologies for going over time.
No,
I might find it.
Yeah. Okay. I have a question.
Sure.
When was this the White Court crater discovered? Is that been there? Like, has everybody known about that for a long time, or was it a recent discovery?
It was a recent discovery. It was found in 2007 by some people that traveled on ATVs, and they sent meteorites into the university. They said, we found a meteor crater. We found meteorites. And the university said, bullshit. And so they sent the meteorite specimens into the university, and the university went, oh my God, they're telling the truth. Most of the time people send in their pet rocks and they're not meteorites, and the universities are just bombarded with crap. But they found these things were actually iron meteorites, and they quickly kept it hush hush. they developed a protected area, and then they announced it to the public.
Okay. So are there questions from either the live audience or the Zoom audience? Richard?
Murray, I have one question. I never met the guy, but my brother-in-law knows Jim Brook, who
Oh,
lives on Tagish Lake. I moved up to the Yukon 6 months after that meteor came in and came down. Scared the hell out of my nephew and all. I thought that was cool. How much did Jim make from all that? Because he did it very carefully and very.
I don't know how much he made from it. I know that he was selling this stuff at fairly good prices. It was, if you want to buy the material now, Tagish Lake costs about $1,000 to $2,000 a gram. So if you can find it. And at the time he was selling it for a lot less than that. And I bought 2 grams of it from him, but it was all little crumbs, and it had disaggregated because it's a very friable meteorite. But other people had managed to get some good specimens out, and I managed to buy a few nicer specimens or trade meteorites for nicer specimens later on. Let's see, I probably should unshare my screen so that I can return it to you. And what I'll do is I'll just hold up a stone. This is a Buzzard Coulee meteorite that I've got in my hands right here. And you can see the black crust, and you can see that gray colored interior of the meteorite. And this is a white quartz iron, and this one's, I've never cleaned it. It's just as found, and this is about 260 grams worth. The Buzzard Coulee is about 65 grams worth.
And there was
Murray,
some, yeah.
Are you aware of a meteorite that would be or was in the observatory at the University of Western Ontario?
I've never been there, so I'm not aware of it.
I have a story similar to yours. In late primary school, I went to the observatory, and my first meteorite that I saw, I was not able to hold in my hand. As I recall, it was about a foot across.
Oh my.
And so, but I must say, our stories sort of diverge there. I haven't, my astronomy career, well, was non-existent, and I haven't ended well.
Okay, and Fred, did you have a question?
I was wondering, where was that huge crater located? 90 kilometers journey?
The 90.
The 90-kilometer, that's the Manikugen, and it's in more or less central Quebec.
Okay.
And it's accessible by road. The Immalaq Crater, it's accessible by aircraft only.
I find it remarkable that anything would be left after the ice ages.
Yeah. Yeah, amazing. Yeah.
So are there any other questions? Okay, well, thank you very much, Murray. Let's just give him a applause. Thank you.